this course consisted of 2 weeks, plus the conference in the middle, plus again 2 weeks. So it was supposed to be a 4-week course, but my lecture at the conference, I said, would be, in a sense, part of the course, but I'll repeat essentially everything essential that was said there and make it complete. In the first part, I talked about the Hurwitz numbers, which were coverings, which counted default coverings of a 2-sphere. So these were some numbers HGD, and I also had some numbers GGD, which counted graphs which had a given number. So here, G and D are the genus upstairs. The genus here is 0. And here, G is the number of loops, so it would be 2, and D was the number of points. And we studied those and found that they had many similarities. They satisfied quadratic recursions and a very similar combinatorics. But then my real goal in the course is to take the related case. I forget now what I called it because I couldn't find my notes of the last lecture, but exactly the same problem if you look at default coverings of a torus rather than a sphere. And so at the end of the second week, I started talking about this and setting up some of the preliminaries. And in the talk at the conference, whose essential points will be more or less repeated in the course, Martin Müller talked about problems of counting so-called flat surfaces. Those are Riemann surfaces together with the differential, and Siegel-Veech constants, and various things that are of interest in dynamics. And then somehow the idea is that although you're counting moduli spaces of modular forms of surfaces of genus G, made with the differential, this flat differential, you can think of the subset of things that cover the standard flat torus. So a square torus, just C modular Z plus ZI. So those are the things that have a square tiling. It's a specific combinatorial structure. And those, as the degree grows for a given genus, they become very dense in the moduli space. And so if you're interested in things like the volume of a certain stratum of moduli space, you can find it by simply counting the number of these combinatorial objects of a given D, which would be finite, and then studying the asymptotics as D goes to infinity. So for the application to the work with Chen and Müller that both Müller and I spoke about last week, we're eventually want to know eventually the asymptotics of these things as D goes to infinity. And that was actually a theme here too. Here we found that if you took the asymptotics of the corresponding generating functions here, which you had to divide by some factorials, but the asymptotics for a fixed genus G as D goes to infinity, after some renormalization in the power series, the Dth coefficient of some power series grew like e to the D, so it had radius of convergence 1 over e, times a power of D, which in the Hurwitz case was, for instance, 5G minus 7 over 2 times a constant depending on G. So in that case, we use the structure of this so-called Lambert space to understand the asymptotics of, for instance, H, I think this is HGD divided by 2G plus 2D minus 2 factorial. Anyway, the numbers that we wanted had asymptotics whose key point, whose key growth was given by a power of D times a constant, and then that constant was really the interesting number and was, in fact, the coefficient of a solution of a Pandavay equation. So at the end of our story here, we'll do the same for coverings of torus. So here we have genus 1. Here we have genus G. And we're going to count these things. So again, I'm not going to go into the details of how you count. I'll just put 1 over the number of automorphisms as always. I talked about this a little last time. We want to find a closed formula for that. One of the main theorems, which I'll give the proof of this time, is that if you fix G and make the generating function of these, that it's a quasimodular form. And then because we know a lot about quasimodular forms, it's a more complicated space than this Lambert space, but nevertheless we get asymptotic statements, and those asymptotic statements are the ones that eventually lead to the results on volumes of strata in moduli space, Siegel-Veech constants, Eskin-Zorich conjecture, and such things. So, but I'll only come to those asymptotic things probably in the very last lecture. So remember that the main goal was a theorem which was stated by Dijkgraaf, and various other mathematical physicists were involved, in particular Douglas and Rudd. So Dijkgraaf gave a way to compute this NGD number here, covariance of the torus, essentially using Hurwitz's original idea for the sphere, but modified for the torus, and made a prediction based on string theory that the corresponding generating series, I'll call it tau, because I want to think of it as a multiforming Q, but tau is in the upper half plane, which means complex numbers with positive imaginary part, and Q is always in the theory of modular forms, unless you're French, is e to the 2 pi I tau. If you're French, of course, it's 2 I pi tau. And then this thing is just the generating function. I could call it FG of Q. I might even, as the physicists do, completely illegally write whichever one I please. But of course, these are different functions. I mean, it's the same function, but of a different variable. So it's the generating function of these numbers. And the claim was that Dijkgraaf, I think, predicted as a special case of mirror symmetry for the case where the target space, the target Calabi-Yau manifold, is an elliptic curve, so a torus. Then you're down to maps from curves to a torus. So he thought of this as kind of part of mirror symmetry. But the specific prediction he made based on his formula and based on a lot of calculations, but I don't think actually proved, was that this is a quasimodular form. I'll repeat the definition in a moment, of weight 6g minus 6. And this was proved by Masanobu Kaneko and myself very shortly afterwards. And actually, the two papers are published side by side, the one where he explains where these numbers are coming from and why string theory predicts the modularity, and our paper giving the modularity. It's a volume in the Berkhäuser Green series. OK, so this is the theorem. And one of the things I wanted to do is to actually give the proof of that original theorem and then the generalization by Bloch and Okounkov that I stated very approximately in my course 2 weeks ago, and then explicitly but very quickly in the lecture last Tuesday. And so I'll go over that, the statement again, and give the complete proof also of that more general theorem. So first, let me remind you how we do this. So to each partition, a partition you can think of as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3, and so on, greater than or equal to 0. So an infinite sequence of numbers, but only finitely many non-zeros. Then the size of lambda, which I'm used to calling n, but for this course it's d, will be simply the sum of the parts. These are called the parts. And one also sometimes writes L is a partition of D using this symbol. So the set of partitions of D is I'll denote by script PD. And the set of all partitions simply by P. So every partition, this is just all partitions, and each partition has some lambda, which is some D, and then belongs to that PD. OK, that's just for notation. So then what we know is that you can associate to lambda several invariants, actually many invariants, but one of them is the dimension. Well, one of them, of course, the size of lambda. That's a very simple one. One which is not so simple is the dimension of the irreducible representation of SD associated to lambda. I didn't, in this course, explain explicitly how you construct that representation, but there was a handout, a one-page sheet, I mean 2 sides, that I handed out that on one side had the statements and proofs of all of the theorems of representation theory, finite groups for general groups, and on the other side did the case of SD and the explicit construction, which is very pretty, of this representation. But just for the dimension, I'll show you in a minute, or remind you in a minute, how you can compute the dimension. Actually, there are 2 different ways. And then another one is, I think I called it nu t of lambda, which you could think of as follows. You let T is the class, the conjugacy class of transpositions in SD. And then you have the associated element, let's call it ET, which is the sum G in this conjugacy class of G, which therefore is explicitly the sum I less than J between 1 and D of the class that you permute I and j. So this is an element of the group ring, and therefore it acts on any representation. So it acts on pi lambda, and so if I take pi of et, this is just going to be a matrix. It's a, I mean, if I choose a basis, and we know by Schur's lemma that because this thing is central, this has to be a constant times the identity. And that constant, I'll denote ut. I could do this for any conjugacy class, but in particular, I do it for this particular conjugacy class for transpositions. And so those are the numbers that are most important for us. Pi of lambda, there are two ways to do it. So there are many ways to describe a partition. This is important. One of them is simply the parts. One is you draw the sort of obvious diagram, which is called the Young diagram. And I want to get my notes. I always use the same example. So as an example, if I take the partition 5, 5, 4, 1. So 5 plus 5 plus 4 plus 1 is 15. This is a partition of 15. And the corresponding, I'll write y lambda for the Young diagram. It means that you make a list of 1, 2, 3, 4, 5. And in this case, again, 5, and then 4, and then 1. Okay, so that would be the corresponding Young diagram. That's another way to think of partitions. Another way that I explained in detail was the Frobenius coordinates. You take the longest diagonal, which is here 3. And so in Frobenius coordinates, you'd have 3, and then here you always put A1 is the arm length, the things to the right of that diagonal square, so there are 4. And then to the right of this diagonal square, there are 3. To the right of that diagonal square, there are 1. So this is A1, A2, A3. And these are, by definition, numbers that are strictly decreasing. Two of the rows can have the same length, but they can't get longer. And since the diagonal is moving one to the right, the AIs are strictly decreasing. And then similarly here, this would be B1, B2, and B3 is the number of blocks strictly below the diagonal. So in this case, it would be 3, 1, 0. So this would be some more numbers, B1 strictly bigger than B2, strictly bigger than B3. In general, A1 up to AR. So those are the Frobenius coordinates, which in this case it would be 3. But in general, it would be R, A1, well, A1 comma, but they're strictly decreasing, non-negative numbers, and B1. And then I also, the very slightly modified ones, I also used A1, which I kind of prefer, 9 halves, 7 halves, 3 halves, 7 halves, 3 halves, 1 half. So these are the numbers A1 tilde, which is A1 plus a half, etc. And I also introduced the notation double F, or kind of to remind you of fermions, is Z shifted by half. So these numbers are now in F plus. They're strictly positive numbers. So in this case, it would be these numbers. And the point of that was that instead of just counting the arm length to be 4, you count then we were ignoring the diagonal square. It's actually more reasonable to think of this thing. And so this would be A1 tilde. A2 tilde would be this one. A3 tilde would be this one, and so on. And in particular, here you see that the size of lambda in the original version was the sum AI plus BI plus 1, because you have to count the diagonal squares. But in the new version, it's just AI plus BI. OK, so that's Frobenius coordinates. And now, in terms of these coordinates, there is a formula, but it's a little complicated, for the dimension. I won't write it in these coordinates. But nu-t of lambda had a very simple formula. It's simply the sum, I from 1 to r, of AI, choose AI plus 1, choose 2, minus BI plus 1, choose 2. So that's obviously an integer. But the more interesting, more natural way to write it, actually, is half of the difference AI tilde squared minus BI tilde squared. You see, the formula simplifies. It's now homogeneous in the A and B tilde. And as already pointed out, this doesn't look very integral. A is a half integer, and therefore it's half of an odd integer. So its square has a denominator 4, but the numerator is 1 mod 8. And similarly, BI squared is denominator 4, but the numerator is also 1 mod 8. So the difference of the numerator is divisible by 8, and this thing is an integer. OK, now for the dimension, maybe it's easiest if I give a table. So here's D, and here's the, I'll list the partitions by their Young diagram. So if it's 2, there are 2 possible Young diagrams, this and this. If there are 3, there are 3. Sorry, I want to do it horizontally first. And if there are 4, there are 5. So there are 3 partitions of 3, 5 partitions of 4, which are given by 1, 2, 3, 4, 1, 2, 3, and 1. So the partition here would be, if I listed the partition itself, would be 1, 2, 1, 1, here 3, here 2, 1, and here 1, 1, 1, here 4, here 3, 1, then 2, 2, then, so this would be 2, 2, this would be 2, 1, 1, and the last one would be 1, 1, 1, 1. Okay, so those are the partitions. The Frobenius coordinates I'm not going to write out. Now the dimension of pi lambda, here it's 1, 1, 1, 1, 2, 1, and here 1, 3, 2, 3, 1. So that I'm right, you can already see simply because for these, that's just the one-dimensional representation. It has to be symmetric, and the sum of the squares has to be n factorial, which is here is 24, and the only way you can do it is 1 plus 9 plus 4 plus 9 plus 1. But the way to get the dimension, there are 2 ways. One is the hook length form, which is very simple. I'll probably skip it, though. But the really nice one is you might remember that I said if you have a representation of the group SD, then you can how do I want to think of it? You take the characters, you can think of this as a representation of R of SD minus 1, because you have a vector space on which SD acts, then the subgroup SD minus 1, which fixes the last of the D numbers, also acts, and then this becomes a sum of some pi prime. But the whole point is that these are distinct. The multiplicity is either 0 or 1. So when you go from one D to the previous one, the space splits into a direct sum of irreducible pieces, but for different ones, and the ones you get are exactly the Young diagrams that you get by omitting any corner square of this Young diagram. So since the space splits as the sum, you see that, for instance, if I take this, it only has one corner. So this one splits into just one piece, which is the one with 3, and so it's the same dimension as here. But here, if I start with this Young diagram, then by removing one corner, there are 2 ways I can do it. I can remove the top right square, or I can remove the bottom square. So I can remove the last square from any row, unless I can't remove this square because it would become too short. It's only the last of several rows of the same length. So in this case, this representation, really the direct sum of these 2, and by induction, this has dimension 2, and this is dimension 1, so the dimension is 3. So it's very easy to compute these dimensions inductively. And finally, if I take my nu t of lambda, well, this will be 0. First, I'll just write them. 1 minus 1, 2, 0, minus 2, and 6, 2, 0, minus 2, and minus 6. So they always change signs. If you flip the Young diagram, if you take the transpose, nu t changes sign. That's why we won't be interested in the sum of the nu t of lambda or the sum of their cubes or fifth powers. That would always be 0. We'll only be interested in the even moments. So here, let's take a typical example. In Frobenius coordinates, this thing, if you draw the diagonal, well, I won't even put the r because it's implicit. You have 1a, which is 5 halves, and you have 1b, which is 1 half, and so you get a half of 25 minus 1 over 4, which is indeed 3. It is, in fact, 3, because it's always a binomial coefficient. The first one is 1, 3, 6, 10. So it was just as well I did that example, what I'd written was actually wrong. And similarly, this is 6. I'm sleepy and not writing what I meant. So here it's the same thing. Here you'd have 3.5. So 1 half, 7 halves squared minus 1 half squared is 49 minus 1 over 8. So that's 6. And similarly, this one would be 5 halves and 3 halves. So that's 25 minus 9 over 8, which is 2, and so on. So these are very, very easy to calculate. Okay, that's my little mini course in partitions and the relevant bits of representation theory of SD. And now I make out of this polynomials, and I remind you first what I did for the Hurwitz sums, or not what I did, but what Hurwitz did in his second paper that I talked about in my second or third lecture. In his first paper is 1891, and then the second he saw that instead of looking at the connected coverings, you could look at all coverings, and that you got a much simpler formula. So if you looked at all coverings, then what you got, so if I look, I think I called it H star, KD, is all coverings, not necessarily connected anymore, coverings of S2, so the 2 sphere, degree D generically ramified, so it means that over every point that is ramified, only 2 points, so simple or generic ramification. But now you have to specify that there are K ramification points. So by the Riemann-Hurwitz formula, if it's connected, then upstairs you have a surface of genus G, like I drew here, and then the Riemann-Hurwitz formula tells you that this K is even, and it's 2G plus 2G plus 2D minus 2. But if I have many Riemann surfaces, then it's, well, K still has to be even, but it's it's whatever it is. So then if we looked at this, then what Hurwitz had seen was that HKD, but now I should get the normalization right, which actually I saw in my notes, in fact in a publication somewhere. Where's it gone? I managed to leave the paper upstairs, my main paper. Well, then I will do it by heart. What you get is the sum over all partitions of D, and then you have to take this mu of pi to the k times the dimension of pi lambda squared. So HKD, it was equal to this up to a factor that now that's what I don't remember, and my notes are upstairs. I think it's 1 over d factorial squared. What we can do is an easy case. If k is 0, this is 1, and then the sum that I mentioned squared would be d factorial, and then indeed this number should be 1. So I think this formula is correct. Okay, so that was the formula. But if I do the same, this was for coverings of a 2 sphere, and then here possibly disconnected coverings, but k ramification points, and a d to 1 covering. If I do exactly the same thing for genus 1, where I don't know if I have a name for it, HK, well, the same for, in fact, I could do any genus. So upstairs, it's not necessarily connected, but downstairs, I have, let's call it genus H. But I'm only going to be interested in H is 0 or 1. Then it was exactly the same formula, and that I explained in my lecture, except this became 2 minus 2H. And I explained that there was a generalized Frobenius formula, again divided by, now there's a power of d factorial that I've forgotten. So the cases that interest, this was the Hurwitz case, this is Hurwitz's formula. And the case that we want for our genus 0, for our genus 1, there won't be any factor of dimension pi at all. So it's actually much simpler. So let me write down a few examples of how that thing looks. So now I think I can erase all of this. So in the Hurwitz case, I mean, I now have my notations from the course. If I sum over k's, the number of ramification points can be arbitrary, strictly positive. The degree is arbitrary, sorry, in fact, it could be 0. And then 0. And then here I take this number hkd squared times x to the k over d factorial y to the d. Then we actually had to take the log of the corresponding generating functions. You had to take cd star of x, y to the d, sorry, CD, I'm confused, sorry. This is already the whole thing. CD star of x is just the sum HKD star x to the k. X to the k. So this, okay. And then this thing counted all coverings, and if you took the log of that, that was the one that gave the Hurwitz numbers. If you just make the corresponding sum, this was the sum HGD over, maybe there's a k factorial here, x to the, now it's 2g plus 2d minus 2, y to the d. The exact forms don't matter for now. I already didn't. Just remind you that the connected ones were the log, and the coefficients of this were the CD star of x. And the claim was that these were always polynomials in e to the x, or maybe e to the x over 2. And the reason for that is that because of this Hurwitz formula here, HKD star is this. So when I divide, yeah, there's certainly k factorial. So if I take the formula that's there, you have to sum over all partitions of D. And then it would be the dimension of the corresponding representation squared. But then each partition lambda contributes mu t of lambda to the k to this HKD star. So when I multiply by x to the k and sum, it becomes e to the nu t of lambda x. So I can call this some polynomial that I even, maybe I gave a name to. It doesn't really matter. I'll call this RD for genus 0 of e to the x. So RD of e to the, of u would be the sum, it's a finite sum, over partitions of D of this dimension, this complicated dimension squared, times u to the power mu t of lambda. Okay, this is, let's say, for genus 0. So that would mean if I took, for instance, 4 as the most interesting case on that board, for 4 you can see there are 5 representations. The first one would be u to the 6th. The next is, but the dimension is 1. The next is dimension 3, so it's 9 u squared. The next is dimension 2, so it's 4 u to the 0, then 9 u to the minus 2, and then u to the minus 6. But if I do exactly the same for genus 1, well, for any genus h, then I would put here dimension of the power 2 minus 2h. But in particular for genus 1, which is what I care about, torus coverings, it's much simpler. There's no coefficient. So here, R4 in genus 1 of u would be u to the 6th plus u squared plus 1 plus u to the minus 2 plus u to the minus 6. So these are sort of the basic polynomials. So here you see that in the Hurwitz number case, so we went through that in detail. At the end, I would sum this RD0 of x, well, of e to the x, the way that I'm writing it, times y to the d. There may or may not be a d factorial. I don't guarantee it because there are so many normalizations. I think there is, because h has a 1 over d factorial. But I have to divide by d factorial again, because if I take k to be 0, if k is 0, this is 1. The sum that I mentioned squared is d factorial, so I get 1. But the generating function has the extra d factorial, so it's e to the x, and the log of that is x, which is as it should be in that case, because the only way that you can get, in that case, k is 2g plus 2d minus 2. The only way to get 0 is if g is 0 and d is 1. So there's only one contribution. So in this case, this would be the, I would want the log of this. That would give me the Hurwitz numbers. But in particular, this is a polynomial e to the x. And so that gives the statement that Hurwitz found that the, for any fixed degree, the corresponding generating function for connected coverings is a polynomial in e to the x. And the one that we want, for exactly the same reason, now, in the u situation, is exactly the same. But now the e to the x is the same formula, but now it's this polynomial, which is a little bit simpler. The coefficients are all, well, the coefficients are not necessarily all 1, because if you take a large partition, these numbers go from mu t of lambda goes from a maximum of d over 2 to a minimum of minus d over 2. So there are roughly d squared of them, but the number of partitions is much bigger. So of course, a given thing will have some multiplicity. So I'm not saying the coefficient will be 1, but for each given partition, you just count it once rather than with the dimension squared. OK, so that's just setting up the group theory. But now we can, in fact, forget about all of this if you believe it. We now have a closed formula for the whole thing. So we now can say that the number that interests us so we had this NGD, which is the number of coverings of genus G to genus 1, the torus, d-fold coverings. And we also had the corresponding generating series, of which we were hoping to show that it's a quasimodular form. So, OK. So now we have a formula for this. If I take the corresponding generating function and take its log, so if I take the sum f g of q, what was the letter y? No. Sorry, fg of tau, I'm calling it. So before we had to divide by 2g plus 2d minus 2 factorial, because that was the number of ramification points. But now the number of ramification points, this we've gone through before using the Riemann-Horvitz formula, if you have a d to 1 generic or simple covering of the torus, then because the Euler characteristic here is 0 rather than 2 as for the sphere, then the number of ramification points here is simply 2g minus 2. It's independent of d. Whereas in the case of a sphere, k, the number of ramification points was 2g plus 2d minus 2. We always had to divide by k factorial. So now the formula is this thing. And so g is now, g goes from 1 to infinity. Now we're counting all coverings. And so because of the thing that I just told you, this will be the sum d from, but you could even take d0, but then rd is just defined as r0 is simply 1. It's the sum d from 0 to infinity, rd. This would have been the same for Horvitz with rd0. It's rd of e to the x q to the d. So this was what Descartes wrote out, but it's basically Horvitz's original idea applied to the case of genus 1 downstairs rather than genus 0. So this is just a reshuffling of all the information that the things we want to take, if we think of it as a two-variable function in Q. So Q, remember, is e to the 2 pi I tau. And this thing, by its definition, is the sum over n and g, ngd, x to the 2g minus 2, maybe with a factorial, q to the d. So we can think of this as a two-generating function, but then you can think of it as a one-generating function whose coefficients are these things we hope are quasimodular. That's a generating function in x, or as a generating function in q, power series in q, and then the coefficients are these polynomials in rd of x, except that I have to take the log because we only want the connected ones. OK, so now we're already rather far and can now actually write down the formula, which is essentially Descartes' formula for how you compute this thing. So now let me go back to my handwritten notes. So in the given case, this would be, if I just take the table at the right for d equals 0, there's nothing for d equals 1. There's only one representation, dimension 1, and the nu is 0. The next case, you see the powers here are u and u inverse. So u is always going to be e to the x. So it's u plus u inverse over 2 factorial squared. So I'm writing it now to make it a little more correct. The next one is u cubed plus, well, if I did the Horvitz case, there'd be 4, but if I do the non-Horvitz case, it would just be 1, and then 36, y cubed. And if I put the 4, it would be exactly the same as we already did for Horvitz. And the next one, I'll just do them all for completeness, u squared plus 1 plus u to the minus 2 plus u to the minus 6. And again, it would have to be this polynomial if we went back to the Horvitz case. That's exactly what I'd done, divided by 4 factorial squared. And then at the end of all of that, we have to take the log. But actually, you can kind of forget the log, because when you take the log, the coefficient of y to the 7 is a homogeneous polynomial of degree 7 in the coefficient of the thing without the log. And so if you show that the coefficient of this thing in a certain degree, in a certain power, y to the x to the 2g minus 2, is a quasi-modular form of the right weight, 6g minus 6, then it's equally true after you take the log. So actually, we can kind of forget the log. What we want to show is that the coefficient of x to the 2g minus 2, well, I can even now call it 2n. In fact, I can even call it m. The coefficient of x to the m in this should be a quasi-modular form whose definition I'll repeat shortly of weight 3m. But of course, if m is odd, the thing on the left is 0 and the thing on the right is also 0. It's not very interesting. And if m is even, we think of m as being 2g minus 2. So what we want to do is show that this thing gives quasi-modular forms. So now I go to that, but first maybe I should remind you, I've used the word today several times. I said it last time, but I haven't repeated the definition. Which one here? Because I think it's correct. Here, the HD had a 1 over d factorial. Well, let's check it, and you'll see, I think, that I'm right. So I'll do it in red, the case for genus 0, so the Hurwitz case. Then I would have to put 4 and 9 and 4 and 9. And now let's set x equal to 0. If I set x equals 0, then u is 1. And then this is just the sum of the squares that I managed. 1 plus 4 plus 1 is 6. 1 plus 9 plus 4 plus 9 plus, sorry, the 9 is in the wrong place, plus 9 plus 1 is 24. So I'll get the log of the sum y to the d over d factorial. I need the extra factorial squared, because this is log of e to the y. That's y. And it's just right, because remember, in the Hurwitz case, the power series was this. So the only way to get x to the 0 is that the genus is 0 and the degree is 1, and then it's y. So I have to get y in that case. So I forget the reason, but I have not made a mistake. You really have to divide by d factorial. Sorry, you're right. You're right, sorry, excuse me. Thank you very much, Stavros. You saved my life again. So he does it all the time. If I were doing the Hurwitz case, which is what I had in mind and had on my notes, I was going to do the next line, I would have these dimensions squared and a d factorial squared. But I told you that if you do genus h, it's some other power, and that power, so when you divide by d factorial, it'll always be, here it's d factorial squared, but in general here it's also d factorial to the power 2h minus 2. So in genus 1, indeed, there's no denominator. Thank you very much. There's absolutely no denominator in the case that I was actually talking about. I apologize to everybody, and thanks, Stavros. I guess I apologize to Stavros, too. So indeed, there are no denominators. The d factorial is to the power is 2h minus 2. So for h equals 1, there is no power. And indeed, you're completely right. And what I want is this. And I would have noticed it in 1 second when I tried to do the calculation. Everything would have failed. But now everything will work. Wait a second, let me just finish. So this is the actual formula, sorry. That's also an extremely interesting question. Yes, in the Hurwitz case, y was y because there was no reason for it to be anything else, but now it's q because there's no reason to be anything else. It's a modular form, it's going to be a modular form, thank you. Y is q. Of course, they're just letters, but q is kind of, and that's e to the, well, it's e to the 2 pi I tau, and u is e to the x. So that's the formula as Descartes gave it, and we want to show that the things here give quasi-modular forms. This reminds me, at some point, I owe the audience another apology, but now I'm in the middle of this story, maybe at the beginning, after the pause. I said one thing that was wrong in my the very end of the last course before the conference, and I want to correct it, but I'll say it later. So, or I can tell you. Okay, I'll say very briefly, if you take the Hurwitz numbers, so with the Hurwitz numbers and then the slightly modified ones, where you divided, so the original Hurwitz numbers of Hurwitz are integers, they correspond to labeling the ramification points. This is the one that you really want, where you count all coverings with 1 over automorphism. We're doing the same thing here. And then the claim was so this number is now has a denominator, but not nearly that big. It's at most d factorial. And if you fixed g, it's not at most d factorial, but if you fixed g, then d factorial hgd had a bounded denominator. And we'd studied the lambda, this lambda space and lambda ring, and I showed that the generating function was, if g was at least 2, was a polynomial in 1 over 1 minus t, where z, I'm just repeating it for those who were here, it was a polynomial in 1 over a certain 1 minus t. The maximal dimension was 5g minus 5. That gave the asymptotics that are mentioned at the top of the right-hand board. But the lowest one was 2g minus 2. And the question is, what is the meaning for an element in the Lambert ring that the polynomial you get is divisible by some large power of 1 over 1 minus t? Here it's the 2g minus 2. And I claimed that that meant that you could actually divide by that power. So that if you divided d factorial hgd by this, g is a fixed number, you divide by d to this fixed positive power, then it will still be a number with bounded denominator. And that's simply not true. I mean, I'd already checked that a month before, decided it was wrong, and then on that day I suddenly said, no, it's right after all in my head. But it isn't. So just remove that from your notes if you were taking notes. That divisibility is not true, and the argument is not right. So what is true is that this thing is in the image of d to the g minus 2 of the Lambert ring, the corresponding power series, but that does not mean that the coefficients are divisible. No, it does not mean, just it isn't true. It's not divisible. It's O of 1 over t to the d at infinity, but it's not a 2g, sorry, 1 over 2 to the 2g minus 2 at infinity. But that doesn't mean anything that I know for the coefficients. I still don't have an interpretation of that, but the divisibility that I claimed is just wrong. And the proof, I mean, it was a very simple argument, but it was simply wrong. Okay, so this is the thing we actually want, indeed a superset with no denominators. So, and as I already said, we don't really care about the log, because I want to show that if I take this thing without the log, I want to show that the coefficient of any given power of x, remember that u is e to the x, so this is an even power series in x. So the coefficient of x to the 2m, I want that the coefficient of any even power of x in this thing is a quasimodular form of weight, in fact, 6m. Well, you could even take m and 3m, but this is even and there aren't any quasimodular forms of odd weight. So we want to understand this thing. And I also want to have to remind you what quasimodular forms are. But for the moment, we still don't need that, because I'm first going to write this following diagraph in a very simple way. But now I want to check what notations I finally decided to use. Okay, so let's, yes? Powers of u or x. No, if you want this, you need a power of x, because that's the generating function. The power of u would not be, it somehow wouldn't make sense. This is to be thought, this thing is going to be a power series in q, whose coefficients are power series in x. So I can just put x and q. But it actually is, that's what you see here, it's actually a power series in e to the u and e to the minus u, but actually even in e to the u plus e to the minus u, because it's symmetric, of q. Sorry, in e to the x, which is u plus u inverse. So it is, in fact, a power series in q whose coefficients are Laurent polynomials in u and actually polynomials in u plus 1 over u. But we want the coefficient of x, and that's just what makes it interesting. Otherwise, it wouldn't make sense at all. You can't pass from one to the other. It's not at all compatible with this operation. So that's what we want. I haven't yet even reminded you what quasimodular forms are, but for the moment they play no role. I want to write this in another way. So this is an extremely simple idea and completely standard. So this power series is the sum, by definition, over d greater than or equal to 0. Oops, somebody's calling me, but they can't. It's not the right time. How can... I'll switch the thing off entirely. So this is the sum, and then using the formula that we already had, I take all lambda in D of u to the power nu t of lambda. That was this polynomial times q to the d. In other words, this is the sum over all partitions of u to the power nu t of lambda times q to the power size of lambda. So that's the expression we want, and again, this u is e to the x. So this is nu t of lambda x to the k, x. So if I want a given x to the k over k factorial, I have the corresponding sum with nu t of lambda to the k. So that's the thing that I'm actually interested in. So now let's look how this looks. If we use the Frobenius coordinates and remember how it looked, the nu t of lambda, remember in Frobenius coordinates, lambda corresponded to several things: an integer r greater than or equal to 0, a collection of numbers in, well, strictly positive because they're half integral in f plus, which remember was half integers but the positive part, a second collection of the same length, also in f plus, and that was in bijection. And so I can write this, since now I haven't missed a single partition. I have r equal from 0 to infinity, and here I have the sum a1 tilde bigger than ar tilde bigger than or equal to 0, and b1 tilde bigger than br tilde bigger than or equal to 0. And then the formula for the thing upstairs was u to the power a half times a1 tilde squared up to ar tilde squared minus b1 tilde squared minus br tilde squared. And then the size of the partition was simply a1 tilde plus ar tilde. Remember, the ar tilde were the areas including half of the diagonal square, and so the sum of the ai tildes was the area above the diagonal, the others was below, and so together they added up to the area of the whole Young diagram, which is of course the sum of the parts, which is d. So this is the formula. And now you have to have a clever idea, but it's a very simple one for if you're used to generating functions. You see, these AIs are completely independent of the BIs. And they're also independent of each other, except that they're different. So we're actually just summing over R tuples of distinct numbers in F+. And any such R tuple you can put in a unique way in decreasing order, but it's just a finite set. And the same for the Bs. So when you have generating functions, the whole magic of generating functions is you always have to make something which is independent. If you have a multisum over many indices, you have to add extra bits and pieces so that the thing that you're summing is a product of things that only depend on one variable at a time. Then the whole thing factors. So here we would like to say the A's are independent of the B's, but they aren't because there are equally many R of this and R of that. So the trick is to put S from 0 to infinity, and then S, and the same thing with S, and then put a kind of a delta RS. You only count the ones where R equals S. But there's a very, very easy way to do that. If I make a new variable, new indeterminate, and I put, when I have my R and my S mentally, this goes to zeta to the power R minus S. Well, zeta to the R has nothing to do with zeta to the S. This is the product of something that only depends on R times something that only depends on S. But at the end, I'll take the coefficient of zeta to the 0. I'll use this notation that I don't really like, but many people use it. The coefficient of, if I have a power series or a polynomial or a power series in x, then square bracket x to the n just means the coefficient of x to the n in that. So if we introduce that, then you suddenly see that this becomes the coefficient of zeta to the 0 in the sum r from 0 to infinity, zeta to the r q to the power, and then the sum a1 tilde bigger than ar tilde bigger than 0, and u to the sum 1/2 sum ai tilde squared, q to the sum ai tilde. But now everything here is completely independent of itself. This, and then the same thing in S. Except that in S, it'll be zeta to the minus S, the same thing, and then u to the minus 1/2 bi tilde squared, and q still to the power plus bi tilde, well, sum. So that's now become a mess, but let me just write out what it is, and then you'll immediately see it. This expression is nothing other than the product A in F plus of 1 plus zeta q to the A, u to the A squared over 2. Because if you take a product of 1 plus a function of A, then in the product, you take a finite number of terms where you take this term, and all the others you take the 1. So we're summing over all finite sets. Every finite subset of the natural number sets, or of F plus, has a cardinality R, which goes from 0 to infinity. If you fix R, it's R tuples. You can put them in decreasing order if it makes you happy, and that's exactly this. And similarly, the other thing is exactly the same with B, but now there's not even any reason to call it B. So I can just put q zeta inverse q to the A, u to the power minus A squared over 2. And so this is just the product. I'll write it more explicitly. It's the product over A taking on the values a half, 3 halves, 5 halves, etc. And so this is the final formula, is you have to take this doubly infinite product, and you take the coefficient of zeta to the 0 in that. And so that's, we still haven't used any modular forms, but that's what this thing is. I'm going to write the whole thing again. So the final statement will be that, well, if I exponentiate the thing that I originally wanted, g from 1 to infinity, x to the 2g minus 2 over 2g minus 2 factorial. Well, I did it in the wrong order, fg of tau. So this is the thing I want. That was this sum over all partitions, e to the power mu t of lambda times x, and then q to the size of the partition. But by this thing, it's also the coefficient of zeta to the 0 in the product A takes on, well, it should be 8 tilde, but I'm now calling it A, takes on the values a half, 3 halves, 5 halves, and so on. So a positive half integral number. And then I have two factors, zeta q to the A. If I do it in terms of x, it would be a squared x over 2. And the second factor is 1 plus zeta inverse q e to the power minus a squared x over 2. Sorry, can you repeat the question if I didn't answer it? Zetas, it's written, it's a new indeterminate. It's a new indeterminate. It's just a letter. In order, yeah, in order, though nobody could read it, but I said it and I hoped everybody had memorized it. Sorry, even I couldn't read it. It's a new indeterminate. So you think of summing over separately RAs and SBs. Then this thing splits up as two products. But then you have to get R equals S, which you do by introducing a factor zeta to the R times zeta to the minus S, and then taking the coefficient of zeta to the 0. But to get zeta to the 0, zeta just tells you how many A's you're taking. So the coefficient here of zeta to the R tells you I take A, R for different A's, A1 up to AR, but since they're different, I can put them in decreasing order. And then here I'll have Q to the sum of the A's, here E to the 1/2 the sum of the A squareds times X, here zeta to the R. But then I want to have the coefficient of 0, so here I need the same R, but of course these numbers are different, and so here I'll have my other sum, and that gives the bijection with the Frobenius coordinates. A very, very simple and very beautiful argument. This is an A that somehow got neglected, yeah. Okay, so we now have a completely closed form. You can put this on the computer. There's no big problem with it. And so this, of course, is just an exponential. So if you're only interested in the coefficient of x to the 6th, because you want g to be whatever it is, 4, then you only expand this up to 1 plus a squared over 2x up to a squared over 2 to the 6th over 6 factorial, x to the 6th plus O of x to the 7th. So it's just a finite sum, and then you just do the thing, have your computer pick out the right coefficient, and you will get the answer as a power series in Q, as many terms as you need. So this already answers the question, how do we compute? And this part is De Graaf. So let's call this even a theorem. So theorem, I think that's basically De Graaf did that part. I mean, it's also mentioned case by some of the others, but it really goes back to Hurwitz's argument, the first part, but then the trick with Frobenius coordinates to put it in this nice form. So this completely computes, and here there'd be no reason to call it tau. I could have used the original FG of Q, as he, of course, did. But now we want to stare at this and see why this thing is modular. But it seems to me it's a perfect time for a pause, because it's just 11. So after the pause, I'll remind you briefly what quasimodular forms are, prove that this is modular, and then go on with the Bloch-Okounkov theorem and why those things are modular, with a much different and actually much simpler proof than this special case. Okay, so now we come to the modular forms part, and maybe I remind you very, very briefly, I went over this 2 weeks ago in the course, and even more briefly in the lecture at the conference, but I remind you very, very briefly. So we have a group which might be SL2Z, which I think everybody knows. It's the set of 2 by 2 matrices. A, B, C, and D are integers and determinant 1. Or it might be the group which is called gamma 0 of 2, which is the same, but B is even. It forms a subgroup, or lots of other things. And then you associate it to it the ring M star of gamma, which is the direct sum of the vector space mk of gamma. And these are modular forms of weight k on gamma. And what that means is that f is in mk if and only if f of tau equals okay, I can say the main point is it's a function which transforms according to this famous formula f of a tau plus b over c tau plus d equals c tau plus d to the k, where k is this weight, f of tau for all tau in the upper half plane and for all a, b, c, d in my group. And then there's a holomorphic growth condition, which we can say that f has some expansion ar q to the r, where the ar has polynomial growth. That already implies that there are no negative r's. For some modular forms reason, there cannot be any. So it's a power series with positive coefficients. I didn't write r from 0 to infinity because actually, in this case, f of tau, this group is generated by tau goes to tau plus 1, and tau goes to minus 1 over tau. And so a modular form for f SL2Z satisfies these two things. But this group is generated, it does not contain that translation, it contains twice that translation. So here you only have f of tau plus 2 is f of tau, and therefore in this case, it's exactly what I said. So any such f will have an expansion, but r is not an integer anymore, but it's a half integer because you only have translation by 2. So in general, you might have fractional powers. It's just a small detail, but in a moment, I'll need gamma 0 of 2. So those are modular forms. And the important thing, as I told in an earlier lecture about modular forms, is that they're wonderful and very easy to deal with, and we know them completely. So we have a complete description of the ring of modular forms after you do a finite amount of work for any group gamma. So given a group gamma, you do some work, and you can find not just the vector spaces, but even the full ring. So in particular, I'll write m star, if I don't put anything else, for the full modular group. And actually, I'll put the q part. So it's m star of this intersected with q of q. We always write q to be e to the 2 pi I tau for convenience. So that's why this was q to the r over 2, because it had translation invariance under tau goes to tau plus 2. So m star will be this. And then, as I said, for any given group, there's a complete description of this ring. And in this particular case, it happens to be free on two generators, E4 and E6. And so I remind you again, we have gk of tau, k is a positive even number, is a constant which happens to be the kth Bernoulli number divided by minus 2k. And then the general coefficient of q to the n for n positive is the sum of the k minus first powers of the divisors of n. And then it's a fact that G4, GK, is a modular form on SL2Z of weight k for all k greater than or equal to 4. And so this E4 is just 240 times G4. That's to make it start with 1, because this coefficient was 1 over 240. And then E6 similarly is minus 504 G6, which is 1. So again, we've made it start with 1. So those two have integer coefficients. In general, the GK always has integer coefficients, as you can see, except for its constant term. But when you divide by the constant term to make the EK, it usually has a denominator, like E12 has a denominator 691, but the first three don't. And you can actually do the first three, you can also do E2. GK exists for every k, so this would be minus 24 G2. So it's 1 minus 24 Q minus 72 Q squared, and so on. But this is not a modular form. If it were a modular form, it would transform by, if I applied the group operation in weight 2. So to make this thing a group operation, you take your function of A tau plus B over C tau plus D, and you divide by C tau plus D to the k, where k is some fixed number. Then that's a group operation. That's an action of SL2Z or gamma, whatever gamma is, on holomorphic functions of tau. And the modular form is a fixed point of that, so it's one where this is simply equal to E2 of tau. But in the k, to f of tau. But E2 is not a modular form. There actually aren't any modular forms. And anyway, E2 can't be a polynomial in things of larger weight. But in this case, there's a correction term, which is 6. I'll do it separately. It's 6 times C over C tau plus D times, well, 6I over pi. Okay, and in general, this is what's called a quasimodular. So that's a quasimodular form. I'll give the complete definition in a moment. So this would be a quasimodular form of weight 2. It's the same weight 2, but it's not equal to that. There's a correction term. So here we have the quasimodular forms, which are the quasimodular forms on that. You can do it for any group, but in particular for SL2Z. And again, if I don't write anything, I mean with rational coefficients. And this will be generated, that's a theorem, not very hard one, by E2, E4, and E6, which are algebraically independent. So both of these rings are free algebras over Q, 1 on 2 generators, 1 on 3 generators. Now, just for completeness, although I don't really care, we could just take that as the definition, those polynomials, but it's very unsatisfying. In general, if you have a quasimodular form on some group K, then it means that if you take 1 over C tau plus D to the K times f of A tau plus B over C tau plus D, then it's a polynomial in C over C tau plus D. Polynomial means a finite sum of powers with coefficients independent of A, B, C, D. So for instance, for E2, you see that the coefficients of the polynomial are 1 and minus 6i, E2 of tau, and minus 6i over pi. They depend on tau, but not on A, B, C, D. That's a slightly different definition for the one Kaneko and I originally gave. This one was pointed out by Van der Naam, that it's equivalent. No, absolutely not. Absolutely not. This is the definition of a modular form. It's a polynomial in C tau. So let's take a simple example. A polynomial has a degree. So if the polynomial has degree p, then we call that the depth. So this we call depth p. And so the case of modular forms is depth 0. There's no correction. So think of the case when this is a polynomial degree tau. Then it's some function g of tau, because it's independent of a, b, c, d. But since it's independent of a, b, c, d, I can take a, b, c to be the identity. Then this is f of tau. So this is f of tau. And so it is modular. It's very surprising. This definition, it looks like you've forgotten something. Everyone, including me, when Werner told me, said, haven't you forgotten the main term? No, it's all there. It's a very pretty definition. OK, we'll never use it again, but I did want to actually tell you what quasi-modular forms are and not just say they're polynomials in E2, E4, and E6, which is completely stupid. So in the given case, as I said, this GK is a modular form of weight k, except for k equals 2, but G2 is I've already written, and therefore E2 is only quasimodular. From this second definition, it's clear that if I have two quasi-modular forms, f and g, of weight k and l, then their product will be also quasi-modular of weight k plus l, and the depth will be the sum. I just multiply those powers here, those polynomials, and so the degrees add. Okay. I should have done this during the pause. I'll remove this completely. So now I'm going to sketch the proof of so this is Descartes' theorem, that the thing we wanted, except I cleverly removed it, the thing that we wanted, which is the generating series of the fg of tau with x to some even power, is the coefficient of zeta to the 0 in this thing. Actually, you'll probably permit me to change the sign of zeta because it looks more like the Jacobi triplet product. Of course, replacing zeta by zeta inverse changes the coefficient of zeta to the n by -1 to the n. But if n is 0, it doesn't change anything. So it's completely legitimate. So this was our goal. We had this double product, and we want to find the coefficient of zeta to the 0 in it and make everything work. So now I suddenly realized that I didn't print out the version I really wanted, and I've actually forgotten. Okay, so what I say, I hope it's right, but it may be slightly wrong. But it'll be right in the notes when they're finally made. There are going to be notes on this course. And so anything that you don't catch now, you can catch later. At least I hope there are going to be notes, and I hope I'll be able to understand them. Okay, so yeah, unfortunately, I didn't print out one of the things. I copied something from the screen, but I'm not sure I didn't omit a factor. And I can't check it because it's on my notes. So the goal, remember, the goal is to prove this theorem. Is the theorem which was stated but not really proved by Descartes and proved by Carnage and myself, that fg is a quasi-modular form on SL2Z, of course, with rational coefficients for every g bigger than equal to 2. We actually know what it is for g equals 1, but it's not interesting. I'll just ignore that. Okay? So there is a point. So I'm being actually slightly sloppy, but I'm not going to go into it. Okay, so let's give us an example. I'll give two examples. One I think I already gave. F2 is 5e2 cubed minus 3e2e4 minus 2e6 divided by the number 2 to the 7th times 3 to the 4th times 5, which is 51,840 if you want this an integer. So that doesn't obviously have integer coefficients, but it does in fact have integer coefficients. There's no coefficient of either 1 or q. Of course, there can't be. There can't be a covering of degree 0 or 1 from a degree 2 surface to a torus, but you can have degree 2. There's exactly 1 up to automorphisms. Then 8q cubed, 30q to the 4th, 80q to the 5th, 180q to the 6th, and so on. So this is a power series with coefficients in q. And the coefficient of qd in this thing, so this would be our number n2d, I guess, has a very nice formula in this case. It's a very simple formula. It's the sum of divisors. E divides, well, d over 6 times the sum, e divides d, e cubed minus de, and you see this solves an integer. Because if d is even, there's no 2, but if d is odd, then e is odd, then these are both odd, the 2 goes away. And if you have a 3, if d is divisible by 3, there's no problem. If d is not divisible by 3, then for some stupid reason, also this is divisible by 3. So in this case, this is an integer. The reason is because this is also, you see, a very important thing that I want to come back to and will very soon is that the map D sends MK actually for any group, but in particular for SL2Z, onto multiforms. D was differentiation in tau, but I divide by 2 pi I to preserve the rationality of the coefficients, so that's q d by dq. In other words, this is the operator that sends q to the d to dq to the d, exactly the same one we used in the Hurwitz story the whole time. The capital D was the sort of key player. So this preserves quasi-modular forms, and so in particular you have the formulas of Ramanujan, which I think I'd written. D of E2 is a polynomial in E2, E4, and E6 of weighted degree 4, so it has to be a combination of E2 squared and E4, and it's that. dV4 is 1/3 E2, E4 minus E6, and d of E6 is 1/2 E2, E6 minus E8, which is E4 squared. Okay, so we have this derivative, and so here it just happens that if you just take E2, that is weight 2. And I'll always write, if I have a modular form, then Fn, just like in the Hurwitz case, I'll mean dn of f. So if I take E2, it is weight 2. But every time you apply d, the weight goes up by 2. So if I differentiate it twice, it is weight 6. If I take E4, it is weight 4. But if I differentiate it once, it is weight 6. And if I take E6, it already is weight 6. And there are 3 of these. So in this case, quasi-modular forms of weight 6 happen to be additively generated by Eisenstein series and their derivatives. That's also true in weights 8 and 10, but no longer true in weight 12, because you have the Cuss form delta. So therefore, for my case, where the weight is reduced by 6, it only happens once. When the genus is 2, I happen to be able to write this, instead of as a polynomial in E2, E4, and E6, as a linear combination. But here the coefficient of q to the d is sigma 5 of d, the sum of the 5th powers. Here it's sigma 3 of d, but I've differentiated, so times d. And here it's sigma 1 of d, but I've differentiated twice. So therefore, this coefficient is a combination of these numbers. And when you work it out, it's that. So that's one nice comment, that here you happen to have a closed formula, but this is only for g equals 2 that you have a closed formula for the nth coefficient. Otherwise, it would involve things like tau of d, the Ramanujan tau function. And another thing is, in general, fg in general is not a power series. In Q, remember the ngd, so you're counting these coverings with one of the number of automorphisms. That number of automorphisms is always finite, but there are denominators. It's just a coincidence that for d equals 2, it's integral. So I wanted to say that so as not to give any false impressions. And so f3, for instance, I won't give f3 as a polynomial in E2, E4, and E6, but just the beginning of its Q expansion. And it starts already with the 12th, q squared, 20/3, q cubed, 102. That is an integer, q to the 4th, but then 2288 over 3, q to the 5th, and so on. So in general, it has a bounded denominator. Any of these things has to have a bounded denominator, here 12, but in general, it's not integral. Just as we had for the Hurwitz numbers, there was a similar statement with a bounded denominator. Okay, so that's just to get the ball rolling. And now what I want to do is to prove, using this Descartes formula, but I already said that if the coefficients of this, if the coefficient of x to the n in this thing is quasimodular of weight 3n, then it's automatically true when you take the log, right? Because the log of a power series is just polynomials in the coefficient and the degree is preserved. So actually, the theorem that we now want to prove, I can now remove this, is that if I write this, so then the coefficient of x to the m, in this, m has to be even, otherwise it will be 0. This will be a modular form of weight 3m, a quasi-modular form of weight 3m. And that's what we're now aiming for. So I'll keep this formula here so I don't lose it, but I have to make some space. So I'll sketch the proof from the original paper that I wrote with Kaneko, because I won't give all the details. It's quite tedious. It's a page and a half if you write out everything. But I'll say the kind of main steps, because both steps are quite pretty. So let's call this thing, but unfortunately, because I changed my notes slightly, I have 2 versions, and I don't know which is. Okay, if I didn't make a mistake, then I define a function p of u. So remember, I was going to use u for e to the x. So then this becomes u to the a squared over 2 and u to the minus a squared over 2. But let me not yet put the zeta in, so let's call this a function of 3 variables. And for some reason that I've forgotten, I put a factor of -1/20. There are various normalizations. What you really want to do with this is make a triple product. So the famous triple product of Jacobi, as the name says, it's a product with 3 factors, and the missing factor would be 1 minus q to the n, which is the Dedekind eta function. And then you have to compensate with this q to the 1/24th. But don't worry, I think this is what I want. So let me define q. This is just a definition. And then the statement here is if I take the coefficient of zeta to the 0, maybe I have to multiply now by q to the 1/24th to get rid of this, and I take the coefficient of x to the m, then this should be a quasimodular form. I think it's correct now. But for the moment, we don't care about the goal. We just look at this expression. And so this expression has 2 nice properties. So the first claim, claim 1, that the coefficient of, so I want to take my p, but I want to write u, as I've already been doing, as e to the x. The q will just be q for the moment. It could be e to the 2 pi tau. And the last one I also want to write is e to the z. So this would be the zeta. I'm going to write as e to the z. Of course, it's a power series then in x and in z. So I can talk about the coefficient of x to the j, z to the l. And the claim is that this thing is a quasimodular form of 3j plus l, but not on SL2z, but on this group gamma 0, 2, which maybe you remember was matrices whose upper right-hand corner was an even number. Okay, that's one statement. And the other statement, maybe I'll write in a minute and prove this one first. Okay, so to do that, I'm going to, remember we had the Eisenstein series. It's probably still written here, or maybe it isn't, but we had gk, which was minus bk over 2k plus the sum. It was this. And so I want to make, this is a modular form of, on SL2z, except if k is 2, you need the tilde. And now I'm going to make 2 Eisenstein series on this slightly smaller group, which I'll call just AK and BK. And so this is GK of tau over 2 minus GK of tau. So it's easy to see GK of tau is already modular on SL2Z. So it's certainly modular on the smaller group, gamma 0 of 2. But because of the 2, you can check easily that tau over 2 also is. All you need is that if you have such a matrix and you conjugate tau by tau over 2, then it pushes this 2 downstairs. But that's still an integer, so you can still apply the modularity. So it's a one-line check that if you have any modular form on SL2Z, you can take the same form with tau over 2, and it's on SL2Z. And so any linear combination of the 2 is also a modular form. So these will now be modular forms. Again, actually modular if k is not 2. Quasimodular if k is 2. Actually, B2 is also modular. Only A2 is not quasi, is quasi. And if you want the actual formulas as the Taylor expansion, it doesn't make much of any difference, but it's easy enough to write them. Then this one has no constant term. And here you again, so both of them look like Eisenstein series. But here, because I'm subtracting this, you're left with only the ones where n over d is odd. And similarly, this one, now there is a constant term, which is 2 to the k minus 1 times bk over 2k. And then the rest of the expansion is d divides n as before, but this time it's d that's odd. So we have two natural Eisenstein series. One d is odd, and one the complementary divisor is odd. And these are quasi-modular. As I said, actually B2 is a true modular form. B2 is a true modular form. And if k is bigger than 2, then they're both modular forms. It's only A2 that is quasi-modular, as it happens. OK, so then a one-line calculation, I won't do it, but you can almost do it. You can see in your head that you could do it, tells you that if I take log of p, p is a product, but log of p is therefore a sum. And now you replace each zeta by e to the z and each u by e to the x, and you just look at the coefficient, and it takes just a minute, and what you find is this: if you take log of zeta and take here the coefficient, again, of x to the g is e to the l, in log of that product, then it is equal to minus 1 over L factorial times, and now there are two cases. If, and you just do it, you just multiply it out, and you'll see immediately that given these formulas, that's what you get. If L is strictly bigger than J, L and J are just two integers. If L is strictly bigger than J, then you get 2 to the 1 minus J times this L minus J first Eisenstein series, AK, which makes sense. L and J here have to have the same parity. Otherwise, it's you get 0 anyway. So L minus J is now at least 2. So we have this A2. And then you take its 2jth derivative, which just means that you have the sum of divised multiplied by something. It's exactly what you do if you just take the log, the sum of the logs, and use that log of 1 minus t is the usual sum t to the r minus t to the r over r. Just put the double sum and compute coefficient. You find that's an immediate calculation. So I'm only giving the result. You get either 2 to the 1 minus j times the 2jth derivative of the Eisenstein series AL minus j, or 2 to the L minus 2j times the j plus L minus first derivative of the j minus L plus second Eisenstein series. And that's if j is greater than or equal to L. But then, since the difference is even, this is an even number that's at least 2. So therefore, in both cases, this is a quasimodular form on gamma 0 of 2. But in one case, there's weight L minus j. But remember, every time you apply d, the weight goes up by 2. That's what I told you. When you differentiate, the weight goes up by 2. It stays quasimodular. So if I differentiate 2j times, the weight goes up by 4j, but it was L minus j, so it's L plus 3j in this case. But in this case, the weight goes up by 2j plus 2L minus 2, which with that is 3j plus L. So in both cases, it's this weight. Just a very, very simple calculation, but with the case distinction. Half of the power series is derivatives of one of the Eisenstein series at one cusp, and the other is the one that's not quite at the two cusps. But there are two. The natural base of Eisenstein series, derivatives of one, if you make this two-variable generating function, then above the diagonal you get derivatives of A, and below the diagonal you get derivatives of B. But that's just a one-line calculation. You just take the log of this and expand it. And that's what you find. So therefore, log P is a power series whose x to the j z to the L coefficient is such a quasimodular form. And then P automatically has the same property for the reason I've been saying. When you take log, each coefficient is a polynomial, which is weighted homogeneous in the coefficients of the original thing. So that takes care of this. And the other statement is kind of pretty. The other statement is that if I write P0 of u zeta to be what we, of u q, to be the thing we want, which is the coefficient of zeta 0 in P of, what was the order? U, q, and zeta. So let P0 be this 0th coefficient. Then you can write P, which is a function of 3 variables, completely in terms of P0 in the following way. It's the sum r in z minus 1 to the r is P0 of u, but now it's u to the r times q. And then it's u to the power, I'm not sure I trust my notes anymore, but let's say it's, I changed my notes in the middle. As I say, there are two normalizations that I've used in two different things, and I changed my mind about what it is, but I hope it's correct. So here's the formula. It's u to the power r cubed over 6, q to the power r squared over 2, zeta to the power r times this P0. So let me prove that as well. So I'll just get the steps. If I take this P of u, q, and zeta, then I have this formula. So what I find from this product is that if I replace, if I don't change u, but I multiply q by u, and I multiply zeta by u to the 1/2 and by q. So if you know Jacobi forms, this is a somewhat familiar transformation, but it's a bit more general. If you make this transformation, then what will you get? Well, the q to the minus 24 becomes uq to the minus 24. And then you'll have the product. Maybe I'm not going to, well, I can write it all out. It's the product over these a's, which are in an f plus. And then one of the terms, when you look at it, a goes up by 1. So it's still an f plus. So in the first term, well, the way I've done it, it's minus. I've read it in the opposite order. A goes up by 1. But in the other term, a goes down by 1. But now if you look at this, when a goes up by 1, it's still a half integer, a positive half integer. So that product, I just rename a to a plus 1. It's the same as this product, except that it starts at 3/2. And therefore, I've left out one term, which is the term for half. So I have to put that in the denominator, zeta q to the half, u to the 1/8. But here, when I take a minus 1, a starts at a half, 3/2. Then a minus 1 runs over all positive half integers, but it also contains minus a half. So I have an extra term in the numerator, which is minus a half squared. So it's, again, an 1/8, q to the probably minus a half, zeta inverse, times the original p. But what? I didn't understand. Where's their mistake? Yes, but I've changed u to uq. Q has changed to uq. Oh, sorry. So you mean that factor isn't there? Thank you. The q is there, so it's u to the minus. Thank you. I didn't catch what you were saying. In fact, in my notes, it's beautifully written that way, but I somehow lost it. Thank you. So it's this, and I think the rest is even correct, except that according to my notes, this should be minus an 1/8 here, because this had a minus sign also. So it's minus an 1/8, but now you're lucky, or not lucky. This and this are the same up to a monomial, so this is simply u to the minus a 1/6, q to the minus a half, zeta minus a half times the original p. So this p has a functional equation, just for this simple reason, because it's a product. When you do exactly this change to uq zeta, everything shifts 1 to the left, so you get one extra term upstairs, one less downstairs, and you end up with this monomial. So now that means this thing certainly has an expansion. So I can write it as the sum PR of u and q a priori times zeta to the r. I could write that if I wanted, because it has a Laurent, and that would be the same notation I used here for p0. But actually, it's convenient, since I already know, because I've done this calculation, what's going to happen. I'm going to include, to make things come out better, the definition of u to the factor u to the r cubed over 6, q to the r squared over 2, in the definition of PR. So this is an empty statement that defines PR. I'm just writing the zeta expansion of p in that way. It's a double Laurent expansion in zeta, and the coefficient of zeta to the r, I'm taking out these two factors to call it PR. Then this functional equation that we just have tells you exactly that PR plus 1 of uq is equal to PR of u and qu. If you just, I've exactly set it up so things work if I haven't made a mistake, and therefore by induction, PR of qu is the same as pu of q and u to the rq, p0 of q and u to the rq, and that's exactly what I claimed. Maybe I lost a minus 1 to the r, sorry, I forgot. So that's, I've just given, very quickly those two proofs, but you see each one is very easy. One used that the product formula gives a functional equation, a very simple functional equation, which means that the Laurent expansion in powers of zeta all reduces to the same function after some change of variables, and the other says that the coefficient of the whole thing. And now there's a kind of a messy induction, complicated induction, which says what we want, that the coefficient of x to the m, I guess to be consistent, I should call it x to the j, in P itself, in P0 is a quasimodular form of weight 3j, but now on gamma 0 of 2. So in other words, the coefficients of P, if you take a double coefficient in x and z, then it's a quasimodular form. So it's a little like topological recursion. As one goes up, the other goes down. There's no simple set. But if you take the totality of coefficients j and l, then you'll see that when you apply this thing here, you keep reducing things, and so you finally get information about the jth coefficient of P0 from some other coefficients of the other PRs, but only finitely many. Everything stays under control. But it's a little messy to write it in a correct way. And so you deduce that the coefficient that we wanted is indeed a quasimodular form of weight 3j, but it's on gamma 0, 2. But now you think of the definition. The definition was this. Here, we always have equally many zetas and zeta inverses. But this is a half integer. That's also a half integer. If you have equally many half integers, the answer is an integer, right? Remember the original q, it was q to the power of the sum of the ai tilde plus bi tilde, but there were equally many a's and b's. They're all half integers, so it's an integer. So therefore, this is a quasimodular form because it's a polynomial in all of these derivatives of Eisenstein series, in principle an explicit polynomial in these derivatives of a and b for each j, some complicated thing, but it does not have, remember those modular forms, this a and b, wherever they've gone, had coefficients which were not power series in q, but in q to the 1/2, because you only had translation by 2. But this one we know has only integer coefficients, and then it's a one-line lemma from the definition of modular forms that if something is a quasimodular form on the subgroup gamma 0 of 2, but happens to also be translation invariant, well then obviously the translation by 1 and gamma 0, 2 generates the bigger group. And so at the end you get this. So it's a kind of an ugly proof because you don't even get what you want, and then you just get it by good luck at the end, which is not how mathematics is meant to go. But that's how it went. Okay, so that's the original proof of that. And now I've spent much more time on that than I planned. So I'm going to say a little more about these things. I'll say one. I really was planning to prove the Bloch-Okounkov theorem in the second half after the pause, but I'm not going to even be able to state it, I think. So now I have to think what's a good thing that I can still do in a reasonable amount. Well, maybe I will remind you a little of the Bloch-Okounkov idea. It was the following idea. If I have any function from P to Q, so arbitrary. So of course the set of such things is just Q to the P, maps from P to Q. It's of course a vector space over Q, but it's a ring if you want, but it is a ring. Well, it is a ring, but that'll play a role in fact. Then I defined the Q bracket. So this I did already in my last lecture in the course, and again in the lecture last week, as the average of the value of lambda over all partitions. But the problem is, of course, so I would like to just say, I take all partitions, and I take 1, and I divide the sum f of lambda by the sum 1. But of course, that would be infinity over infinity. And so what you do is you put a weight, like you do in statistical mechanics. Think of Q as e to the energy over temperature. So the energy of a state would be just the size of the number of which it's a partition. And here I have this. So we take a Q, and if you want, this is either a formal power series. For me, it'll be a formal power series, or holomorphic in Q less than 1 if f is, let's say, if f is small enough, which all of our functions, in fact, will be. So if it grows polynomially in the size of lambda at most, then there's no problem, but which will always be the case. But you can do this for an arbitrary function. You get a formal power series. And this is called the Q bracket. So the theorem that we've just proved here exactly says, so let's take some examples. So the Q bracket of 1 is, of course, 1, right? Just by definition. Now, how about the Q bracket of Q2? So I haven't told you what Q2 is. How about the Q bracket? Well, maybe I will tell you what Q2 is. I mean, I actually did tell you last time, but I'll say it again. Q2 of lambda is the size of the partition, but it turns out to be a very good idea to subtract a 24th. Okay? So let's do this one. So this will be the sum d from 1 to infinity, d from 0 to infinity, well, 0 to infinity. And now if lambda is a partition of d, then this number is d minus 1/24th. And I have q to the d, but of course the number of partitions has to be inserted. So p of d is the number of partitions of d. So it's the cardinality of the set of partitions of p of d. And of course, Euler found the formula for that, and we know very well that the sum pd q to the d, d from 0 to infinity, excuse me, is, and it's a trivial proof, the product 1 over 1 minus q to the n from 1 to infinity. Let me remind you of the trivial proof. If you write this factor as an arithmetic series, 1 plus q to the n plus q to the 2n, then when you take the coefficient of some d, you're writing d. This is this thing with n equals 1, 2, 3, and so on. So you're writing d as some multiple of 1 plus some multiple of 2 plus some multiple of 3, which exactly means you've shown so many parts of size 1, parts of size 2, and so on. So it's partitions. This was the original place in mathematics where generating functions were first introduced, when Euler realized that these partitions that he'd been counting, you could make into a power series, and you got this nice fact. So it's also a fact that there's a famous function called eta, but that is the q to the 1/24th. That's why I took it out a moment ago. N from 1 to infinity. And this thing is a modular form of weight 1/2, but I haven't defined that. But anyway, that's what it is. And one way to define it quickly is to say that if I took the 24th power, 24 times 1/2 is 12, then this is a modular form of weight 12. And since we know that all modular forms are polynomials in E4 and E6, it must be a combination of E4 cubed and E6 squared because it is weight 12. And since it is no constant term, and these have constant term 1, it must be proportional to the difference. And so this is 240 times 3. And the next one is minus 504 times 2. And so the 720 minus 1,008 is 1728. So just knowing that it's a polynomial in E4 and E6 and has degree 12, and the first two coefficients already tells you it's this, which is some famous identity of I don't know who. So, So there's this eta function, and the denominator that I had there is eta. But now if we look at this, then you see that what's written downstairs is 1 over eta, or more precisely, it's q to the 1/24th over eta of tau. That's the denominator. But actually, I don't have to be so complicated. Because this was q to the d. Instead of putting that, I can put minus 1 over 24th right away. After all, that doesn't change the fraction. Now the denominator is eta inverse. But the numerator is d of eta inverse, right? Because d of q to the anything is anything times q to the anything. So here, anything is d minus 1/24th. So this is the logarithmic derivative of eta, which is, well, that's now a one-line check. This is exactly E2, E2 over 24, minus E2 over 24. If you want, I can do that calculation. It's trivial. Eta is given as a product, and so if I take d eta over eta, that's the logarithmic derivative, then I get minus d over eta is minus 1 over 24th plus the sum, and then you take the logarithmic derivative here, it's n q to the n over 1 minus q to the n. And this was exactly the definition of G24, of G2, excuse me, which is minus 1/24th E2. So maybe it's plus because of the eta, so it's probably plus 1/24th because it's eta inverse. So that's the very, very simplest case. So if I define Q2 of a partition to be what I wrote, So I'll write again what I've just said. Now we don't need any of this. So if I define Q2 of a partition to be lambda minus 1/24th, then we just check that the Q bracket of that Q2 is E2 over 24, which is a quasimodular form of weight 2. Now, if I define Q0 of lambda to be 1, then Q0 is, the Q bracket is 1, which is also a quasimodular form of weight 0. And if I define even stupider Q1 of lambda to be 0, then Q1Q is 0, which is certainly a quasimodular form of weight 1. Not a very interesting one, but there aren't any very interesting ones because that space is 0. Okay, now let's do a slightly more general calculation. Let's think here what happens if you take any f and you multiply by Q2. Well, that would be the sum. Here I take Q2 of lambda, which is lambda minus a 24th, times f of lambda times q to the lambda, divided by the sum lambda q to the power lambda. And again, if it makes me happy, I can divide numerator and denominator by q to the 1/24th. But then, for the same reason as before, this is, here I have this infinite product, so this infinite product. Here, this thing is the derivative of the d derivative of what it would be without that factor, and that is fq times, let me just call this product p for product. So p is the sum q to the lambda, which is the product 1 over 1 minus q to the n, which, as we just saw, is q to the minus 1/24th. Sorry, I even put the minus 1/24th. So this is q to the minus 1/24th over the product 1 minus q to the n, and it's therefore 1 over eta. Actually, then I don't have to give it a name. I'll just give it the name 1 over eta. So again, the denominator here is now 1 over eta. But the numerator is d of the sum f of lambda times q, but that's 1 over eta times the original q bracket. But d is a derivation. So when I differentiate, I either take the derivative of eta over eta, what we already saw, that's E2 over 24, times the given q bracket, or I take 1 over eta, but then this cancels, times d of this. So if you take the q bracket of any function at all on partitions, and then you take the q bracket of q2 times the same function, then that is the sum of two terms. One is E2 over 24 times the original q bracket of f, and the other is the derivative, this d derivative of the modular form. So in particular, if fq happens to be quasimodular of some weight k, then q2 times f is also quasimodular of weight 2 more, because you either differentiate, which raises the weight by 2, or you multiply by E2 over 24, which also raises the weight by 2. So that's part of the structure, and therefore, if I use this, we also get that q2 to the nth q is also a quasimodular form of weight 2n for every n. And I even have a little table, if I can find it. So, sorry, this was minus E over 24, if I did it right. Let me use, as I already once told you I might, P, Q, and R is Ramanujan's notations just because it's shorter for E2, E4, and E6. Then here's n and Q2 to the n. So for 0, it's 1. For 1, it's minus a 24th P. For 2, I have to find it, it's 1 over 576 times minus P squared plus 2Q. And for 3, it's, where's it gone? Q2 cubed. It's 1 over 13,824 times, you just do this by applying inductively the thing that I just showed you, differentiating, and using Ramanujan's formulas for the derivative. So that's already a few examples. And then finally, Q3 of lambda is going to be nu t of lambda, the same function we took. And so Q3 to the m, the Q bracket, that's exactly what we proved. That's exactly the theorem that I proved before. This, if m was 2g minus 2, if m was m actually, it corresponded to the not necessarily connected covers of a torus with two m ramification points. Sorry, with m ramification points, but m has to be even. So actually, it's the same k we had before, but I don't want to call it k, I'll call it m. Then this one was a modular form of weight 3m. But of course, it's 0 if m is odd, because there are no quasi-modular forms of odd weight. And also Q3, as we saw before, is odd. So this is the beginning of the Bloch-Okounkov theorem. The Bloch-Okounkov theorem, which I now won't state, I'll say it at the beginning of next time. I already gave the definition, but I'll repeat it next time. Gives further explicit functions Q4, Q5. And the theorem says that if you take any polynomial in these QKs, you always get a quasi-modular form. What I want to do for the rest of today is something that I told in the lecture on Tuesday, but just with no proofs, and very, very briefly. So I'll say a few more words about that, and then that's the end of today's lecture. So the fact, which is very surprising, so the Bloch-Okounkov theorem, which I'll state again and prove next time, says that if f is any polynomial in certain universal functions, Q1, Q2, Q3, which are completely explicit in terms of Frobenius coordinates, and of which I wrote out the first four explicitly, Q0, Q1, Q2, and Q3 here, then Q is a quasi-modular form on SL2Z, and the weight is the right one. If QK has weight K, and it's homogeneous of weight K, then you get weight K. But in fact, there are many, that's what I said in the lecture on Tuesday, there are many more. So there are many more functions, f, which are not polynomials in these particular Q1, Q2, Q3, but you still get modular forms. So the easiest example, and that I'll prove for you, I gave it in the course, but I just said it's very easy, is take SP of lambda to be the pth moment, pth part moment. So this is the sum lambda I to the p, where lambda, remember, has parts, lambda 1, lambda 2, and so on greater than or equal to 0. So I goes from 1 to infinity, but of course it's a finite sum if p is positive. Then the claim is that SP, well, let's just do it. So I'm going to now compute what you get for this SP. So, of course, I can write SP of lambda as the sum lambda I to the b. I can also write it as the sum m from 1 to infinity, Rm of lambda, m to the p. Rm of a partition is the multiplicity of m in lambda. In other words, I write lambda as one often writes it 1, 1, 1, 2, 2, 2, so with powers, not meaning that you multiply those numbers. And the exponents are R1 of lambda, R2 of lambda, so on. I didn't write the lambda. Okay? So by definition, if you count how many parts there are which are m, there are m of them, and then the part to the p is m to the p. So we can write it like that. So now, that means, remember that when you take the Q bracket of something, you could also write this as the sum d from 0 to infinity, Q to the d. And then it's simply the sum f of lambda, where lambda is a partition of d. So it's a very crude invariant. What you're doing with your function is to add up all of the values for all partitions of a given d. It's only the average value, or the total, that you're seeing. So it's a very crude invariant. So here, if I take the sum lambda equals d, so in other words, lambda is a partition of d, of this SP of lambda. Now I'm looking at the notes. Then I can also write this as the sum m from 1 to infinity, nm of d, m to the p, and this is the number, nm of d is the number of partitions of d, sorry, it's the number of parts of size m in any partition of d. So you take all partitions of D and you look how many times, for instance, 5 occurs. And if 5 doesn't occur, you don't count it. But if 5 occurs as a part 3 times, you count it 3 times. So you count partitions according to the number of times they take D. So in other words, this is the sum, lambda divides D of Rm of lambda. So I'm just putting things in a different order. Lambda equals D. Okay? So now, on the other hand, now let's make the generating function of this Nm of D. So m is fixed. It's 1, 2, or 3. D goes from 0 to infinity. So we're looking at all partitions. Every partition is a sum of a certain number, R1, R2, and so on. That's the number of ones, the number of twos, so the partition is now in increasing rather than decreasing order. It's R1 ones, R2 twos. So the Ri's are just arbitrary integers, only finitely many are non-zero. And then the size of the partition is R1 plus 2R2 plus 3R3. But how many times am I counting? I'm counting it Rm times. So the multiplicity here is this Rm. But now this is a typical and very easy generating series calculation. This is equal to the product. For every I different from m, I just have q to the IR. But if I is equal to m, then I've r times q to the mr. But on the other hand, the sum q to the IR is just 1 over 1 minus q to the I. Whereas this thing is q to the m over 1 minus q to the m squared. So this is simply q to the m over 1 minus q to the minus m times the product over all I, equal or different, of 1 over 1 minus q to the I. But what does that mean? That means that Nm, the Q bracket, remember the Q bracket is you sum with, sorry, I don't want to write like that. Well, it does mean that, but what it means now is that SP, the sum, is equal simply to the sum m from 1 to infinity. And now I have to take this weighting factor, which is m to the p. And now I take the generating function of Nm of D, which is this, which is q to the m over 1 minus q to the m. And then I have to multiply by this product of everything. But in the q bracket, you divide by that product. And so this is the whole answer. So the q bracket of SP is just the sum m to the p q minus 1. And so you see that I could also write this by expanding this to geometric series as the sum n from 1 to infinity, sum d divides n, d to the p, q to the n. And so you see that if k is a positive even number, and I take sk minus 1q, then I get this thing. This is exactly sigma k minus 1 of q. That was exactly, I'll write it in q, although it should be in tau. This is exactly the kth Eisenstein series, well, in tau or in q, except that I've subtracted the constant term, 0. This means q equals 0, which is the constant term, because it's only the positive part. So this is a quasimodular form. I mean, this is quasimodular of weight k, and this is quasimodular of weight 0. So the whole thing is quasimodular of mixed weight. There's a constant and a part of weight k. So that's a kind of a really, really simple example. We did it completely by hand, and that's what you got. So I wanted to give one more example. Now, I was going to sketch the proof, but I won't. But maybe they'll appear in the notes. Maybe they won't. I'll put it here. And then there'll be a much more interesting example next time that I mentioned in the lecture on Tuesday. That'll be the hook length moments. But I won't do the hook length moments here. But instead, I'll take one more relatively... Wait. It's after. Then I'll just state the theorem and not give the proof, but just very, very briefly. So let P equals any polynomial in two variables. And I define AP, the bracket, as the sum. I take all hooks. So here's the Young diagram. I take the cells in the Young diagram. Any cell, I make the diagonal, and then there's an arm length and a leg length for that cell. I did it before only for the diagonal. So this would be A tilde, and this is B tilde, which are, again, half integers. And now I take the polynomial in the arm length of S, but it's this tilde, so it's a half integer, and minus B tilde of S. And then the claim is, so that's that's a theorem that I found, but it's an easy consequence of the theorem in the literature, theorem that for any polynomial at all, let's say with rational coefficients, so P of X, P of AB is a polynomial in A and B with rational coefficients, then the Q bracket is always, it has mixed weight in general, but it's always a quasimodular form. And it's almost never in the Bloch-Okounkov ring. And also the things that have this magic property do not form a ring. If you take one of these SPs, which are not in the Bloch-Okounkov ring, which they all aren't except the first one, or one of these, which are almost never, if you take that and multiply by another one or by something that is in the Bloch-Okounkov ring, it no longer has modular or quasimodular Q brackets. So it's not a ring property. That just happens that in the original theorem, you took the ring generated by Q1, Q2, Q3 up to infinity, and they all had this modularity property that the Q bracket is quasimodular. But here are two completely different examples, polynomials in the arm and leg lengths of the cells, and this thing, and those are completely different examples. So next time I might sketch a little bit of the proof of that and Bloch-Okounkov, and then I want to go on to the asymptotic things. Whoa.